Hold up your hand in the dark for a moment. The atoms in it are almost as old as the universe, forged in the first few minutes of everything and inside the furnaces of dying stars. That alone is an age almost beyond meaning. And yet, passing straight through that hand right now are things older still. Particles set loose 1 second after the beginning are streaming through your skin as though it were not there. A faint tremor in the fabric of space, one that may reach back before the Big Bang itself, is washing through you as you lie still. We are taught to look outward for the oldest things, toward distant galaxies and ancient light. But tonight we are going to count down 10 of the most ancient objects and relics in the cosmos, from a single star that appears older than time to a field that came before the beginning. And we are going to find that some of the oldest things there are have been with you the whole time. Get comfortable and let yourself settle in. Hit subscribe if this is your first time here, because by the end of this, the oldest things in the universe are going to feel a great deal less far away than they do right now. Now, let's slowly ease into this. Part 1. The star that shouldn't exist. There is a star in the constellation Libra that carries a number it should not be allowed to carry. You cannot see it with your eyes. It sits about 190 light-years from where you are right now, a faint ember among thousands of brighter ones. And if you looked straight at its patch of sky tonight, you would never guess that it holds one of the quietest problems in all of physics. Astronomers gave it a plain catalogue name, HD 140283, but the name that stuck is older and stranger. They call it Methuselah, after the longest-lived figure in ancient scripture, because when they first measured its age, the number came back older than the universe itself. In the year 2000, a team led by Howard Bond at Penn State University pointed the Hubble Space Telescope at this faint star and worked out how long it had been burning. The answer they arrived at was about 14.5 billion years. Now hold that against the age of the cosmos. The universe, as best we can measure it, is about 13.8 billion years old. That means the first measurement of this star placed its birth roughly 700 million years before there was a universe for it to be born into. A child older than its own mother. A book written before the paper existed. It is the kind of contradiction that should simply end the conversation, because it cannot be true, and yet there the star sits, burning steadily, indifferent to the trouble it causes. Let me be honest with you from the very first minute, because this whole video is going to ask you to hold two things at once. The honest reading of Methuselah is not that we have found a star older than time. The honest reading is that dating a single star is genuinely, maddeningly hard, and that the number almost certainly has more give in it than the headline suggests. But I want you to notice something before we reassure ourselves too quickly. The only thing standing between us and the impossible is the size of our uncertainty. And that is a strange place to keep the beginning of everything. To understand why this star is old at all, you have to look at what it is made of. Methuselah is what astronomers call a subgiant, a star in a particular late chapter of its life, and its chemistry is almost empty. It contains almost no iron. It contains almost none of the heavier elements that make up so much of a younger star like our Sun. And that emptiness is a kind of birth certificate. The heavy elements in the universe were not there at the start. They were cooked, slowly, inside generations of stars, and scattered into space when those stars died. A star heavy with iron formed late, out of gas that had already been enriched by the deaths of others. A star with almost no iron formed early, out of the thin primordial gas that existed before many stars had lived and died at all. Methuselah is nearly empty of heavy elements, and so it must have formed when the universe was very young, in its first chapter, before the great enrichment had really begun. So the star is old. Nobody serious disputes that. The trouble is only ever in the last stretch of the number, in whether it formed at 13 billion years ago or 14.5 billion years ago, and that last stretch is exactly where our tools go soft. In 2013, astronomers went back to the problem with better data on the star's distance and its composition, and they brought the estimate down. The new figure was about 14.46 billion years, with an uncertainty of around 800 million years in either direction. And people breathed a sigh of relief because now, finally, the star could be younger than the universe. If you take the low end of that error bar, Methuselah formed comfortably after the Big Bang, and the paradox dissolves. But look closely at what that sentence actually says, because it is doing something quiet and important. It does not say the star is younger than the universe. It says the star can be younger than the universe if we lean on the generous end of our own imprecision. The central value, the single best number we have, still sits above 13.8 billion years. It still, taken at face value, places this star's birth before the beginning. We rescue consistency only by admitting that we're not sure, and by letting the not sure reach all the way back past the edge of time. I want to sit in that for a moment, because it sets the tone for everything that follows tonight. We talk about the age of the universe as if it were carved into something. 13.8 billion years. We say it with confidence, but that number is not carved into anything. It is a measurement, assembled from other measurements, each with its own softness. And the ages of the oldest stars are measurements too, assembled differently with their own softness. When two independent clocks that should agree drift apart by hundreds of millions of years, the correct response is not panic and it is not dismissal. The correct response is humility about the clocks, and humility about the clocks is a much bigger admission than it sounds, because those clocks are the entire basis for the sentence we keep repeating about when everything began. Imagine for a moment that you are standing outside tonight, on a clear night, looking up toward Libra. You will not find Methuselah with your eyes, but you know now roughly where it hides. The light entering your eye from that direction left the star about 190 years ago, around the time of quiet, lamplit rooms and horse-drawn roads, long before you or anyone you have ever met was born. And the star that emitted that light was already impossibly old when it did. You're looking at ancient light from an ancient thing, and the simple act of tilting your head back becomes an act of looking backward in time, further back than you can really feel. The point of light is small, the age behind it is not. And somewhere in the gap between those two facts is the first crack in the story we tell ourselves about the beginning. There is something fitting in the name they chose for it. Methuselah in the old scriptures is the figure who lived longer than any other, nearly 1,000 years, a byword for age beyond reason. To hang that name on a star is to admit quietly that the thing unsettles us, that it seems to have outlived the world it belongs to. And this particular star is a wanderer in another sense too. It does not belong to the calm, flat disk of our galaxy, where the sun drifts along its orbit. It is a member of the old galactic halo, the population of ancient stars that loops through the galaxy on long, steep paths. And right now, Methuselah is simply passing through our neighborhood on one of those long arcs, moving quickly against the background of younger stars, a visitor from an older chapter of the galaxy's life, on its way through and then gone. I think the reason Methuselah unsettles people so much is that it quietly exposes how our confidence about the age of everything is built. When we say the universe is 13.8 billion years old, we're not reading that number off a cosmic clock face. We're inferring it from how fast the universe is expanding, from the detailed pattern in the ancient background light, from the measured amounts of the lightest elements, all folded together through a model. It is a superb piece of work, and it hangs together remarkably well. But it is still an inference, a conclusion drawn from a web of measurements, each of which could in principle shift. And on the other side of the ledger, the ages of the oldest stars are inferred by a completely different route, through the physics of how stars burn. When those two independent inferences brush up against each other and very nearly cross, as they do with Methuselah, it is a reminder that both numbers are human constructions, careful and hard-won, but not carved into the sky. The beginning of everything is not a line we have seen. It is a line we have calculated. It helps to understand how astronomers even try to put a number on a star's age, because the method reveals exactly where the softness comes from. You cannot simply read a star's age off its surface. What you can do is measure its brightness, its temperature and its chemistry, and then compare those against detailed models of how stars of different masses evolve over time. A star like Methuselah, in its subgiant phase, is at a particularly telling moment in its life, a stage where its brightness changes in a way that is fairly sensitive to its age. So you take the model, you fit the star's measured properties to it, and out comes an estimate. But every step in that chain depends on knowing the star's true distance, because distance is what turns how bright the star looks into how bright the star actually is, and getting distance wrong throws the whole calculation off. That is precisely what shifted between the year 2000 and 2013. In the years between those measurements, better data on the star's distance became available, along with refined figures for its composition, and when those went into the models, the estimated age came down from about 14.5 billion years to about 14.46 billion years. The number moved not because the star changed, but because our knowledge of it sharpened. And that is the quiet lesson hiding inside the whole affair. The age of a star is not a fact we read. It is a conclusion we build out of other measurements, each carrying its own uncertainty, and the final answer is only ever as firm as the shakiest link in the chain. Methuselah is also not the first time the universe seemed to contain something older than itself. In the 1990s, astronomers studying the oldest star clusters in our galaxy, the globular clusters, kept arriving at ages that came out uncomfortably close to, and sometimes older than, the best estimates for the age of the universe at the time. For a while there was a genuine crisis, a real tension between the age of the contents and the age of the container. That earlier crisis eased when our understanding of cosmic expansion improved, when the discovery of the accelerating universe and better measurements of the expansion rate revised the age of the cosmos upward and the ages of the clusters slightly downward until the two finally fit. The lesson from that episode is worth carrying. These tensions have appeared before, and they have been resolved before, usually by discovering that one of our numbers needed adjusting. But notice what that history really tells you. It tells you that the age of everything is a number that has moved more than once and been argued over and revised. It is not a fixed wall. It is a working estimate. There is, of course, a stranger version of this story that circulates online, the version that says scientists have quietly found a star older than the universe and are covering it up, hiding a discovery that would break the whole Big Bang picture. And I understand why that version is tempting, because it feels like a secret. But it does not survive contact with how the science actually happened. The age of Methuselah was not hidden. It was published openly in the scientific literature, headline and all, precisely because it was startling. The revision was published too. The uncertainty was published. Nobody buried this. If anything, the reason you have heard of Methuselah at all is that astronomers found the tension fascinating and said so out loud. The grounded truth is less like a conspiracy and more like a confession, an open admission that our tools for dating the oldest things have limits we cannot yet fully close. Here is what I keep coming back to with Methuselah. Even if the mainstream reading is right, even if this star is merely very old and not truly older than the cosmos, the episode has already shown us something we do not like to look at directly. It has shown us that the timeline of everything is not a wall. It is a negotiation between imperfect instruments, and the negotiation can, on its worst days, hand us a number that predates the beginning. If our best method for dating the universe and our best method for dating its oldest star can disagree by that much, then how firmly do we really know when or whether everything actually began? That is the question Methuselah leaves burning, 190 light-years away, in silence. And it is only number 10. The list only gets stranger from here because the next objects do not lean on measurement error at all. They are exactly what they appear to be, and that is the problem. Part 2. The Giant Born Too Soon. If Methuselah troubles us because our clocks might be wrong, the next object troubles us because our clocks are almost certainly right, and the thing they are measuring should not be possible anyway. To find it, we have to look much further away, and therefore much further back, because in this universe distance and time are the same measurement wearing two different faces. When you look at something billions of light-years away, you are not seeing it as it is. You are seeing it as it was, when the light left, and the further you look, the deeper into the past you fall. In 2017, astronomers using the Magellan telescopes in Chile found a quasar. A quasar is one of the brightest things the universe knows how to make, a colossal outpouring of light from the region around a feeding black hole, and this one carried a catalogue name, J1342 plus 0928. Its light had been travelling for more than 13 billion years before it reached the mirrors in Chile. That means we were seeing this object as it existed when the universe was only about 690 million years old. In cosmic terms, that is infancy. The universe had barely begun to make galaxies. The first stars were still a recent event, and already, sitting at the centre of this quasar, was a black hole with a mass of around 800 million times the mass of our Sun. Take a slow breath, because you have to feel the weight of that number to feel the problem. 800 million suns collapsed into a single gravitational well, already assembled and already feeding, when the universe was less than 1/20th of its present age. The object itself is not in dispute. We can see it. We can measure the light, and from the light we can weigh the darkness at its center. What is in dispute is how it could possibly be there so soon, because black holes do not simply appear at that size. They grow, and growth takes time, and there was almost no time. Here is the rule that makes this so uncomfortable. Black holes get bigger by pulling in surrounding matter, but they cannot pull it in as fast as they might like. As matter falls toward a black hole, it heats up and blazes with radiation, and that radiation pushes outward on the very material trying to fall in. There is a ceiling, a natural speed limit on how fast a black hole can feed, before its own brilliance starts blowing its next meal away. Physicists call this the Eddington limit, and when you take a black hole of ordinary size, the kind you would get from a single collapsing star, and you let it grow at the fastest rate the Eddington limit allows, it still takes far, far longer than 690 million years to reach 800 million solar masses. The arithmetic simply does not close. You cannot get from a stellar sea to this monster in the time available. The universe was not old enough to have built the thing we are plainly looking at. So what do you do when you can see something that could not have formed? You are forced to conclude that it did not form the ordinary way, and that conclusion pushes the real mystery back into a time we cannot observe at all. Something must have given these early giants a head start. Something must have planted seeds far heavier than a single dying star, and planted them very early, in the first few 100 million years, possibly during or even before the period astronomers call rionization, when the first light was still burning its way through the fog of neutral gas that filled the young cosmos. There are serious ideas about what that head start could have been. One of the leading ones is called direct collapse. Instead of a star forming, living and dying to leave behind a modest black hole, an enormous cloud of primordial gas skips the whole stellar life cycle and collapses straight into a heavy black hole from the start, tens of thousands of times the mass of the Sun in a single event. That gives you a much bigger seed to begin with, and a much better chance of reaching monstrous size in a hurry. Other ideas reach for even earlier conditions, for seeds laid down in an environment we have no way to look at directly, in physics we have not yet fully written. Notice what has happened to the question. We started by asking how a specific black hole got so big so fast, and the honest answer has quietly relocated the mystery to the far side of a wall. This particular quasar is not older than the universe. It formed well after the Big Bang, and there is no paradox in the object itself. But the seed that made it possible, the thing that gave it its head start, seems to belong to an era we cannot see into, an era whose conditions we can only infer from the giants it left behind. We are like people who walk into a room and find a fully grown oak, in a world where we thought all the acorns had only just been planted. The tree is real, the tree is measured, and the tree is telling us that something was happening in the soil long before we thought anything could. To feel why the timing is such a problem, it helps to picture the era this quasar lived in. 690 million years after the Big Bang, the universe was still emerging from the long darkness we will visit later on this list. The first stars had formed, the first galaxies were assembling, and light was still fighting its way outward through a lingering fog of neutral gas that filled space, a period astronomers call rionization, when the young cosmos was slowly becoming transparent. This was not a settled, mature universe with billions of years of history behind it. It was a construction site, barely begun, and yet standing in the middle of that construction site, already finished, already colossal, was a black hole 800 million times the mass of the Sun, blazing as a quasar so bright we can still catch its light across almost the entire span of cosmic time. It is the equivalent of walking onto the foundation of a house on its first day and finding the chimney already built, tall and complete, with smoke already rising from it. The strangeness compounds when you remember that a black hole does not simply need matter to grow, it needs time to process that matter, and time was the one thing in desperately short supply. Even feeding at the absolute maximum rate the physics allows, without a single pause, a black hole starting from a modest stellar seed cannot climb to this mass in the years available. Something had to cheat the clock. Either the seed was born far larger than any dying star could leave behind, or these early black holes found a way to feed faster than we thought possible, briefly exceeding the usual limit in bursts or some combination of both. Each of those answers pushes the real action earlier, into the first hundreds of millions of years and toward conditions we cannot directly observe. The quasar is a signpost, and everything it points at is hidden behind the fog. It is worth pausing on just how bright a quasar is, because the brightness is the reason we can see this thing across almost the entire width of observable time. A quasar is not a star. It is the blazing region around a supermassive black hole that is actively feeding, where gas spirals inward, compresses, and heats to temperatures that make it pour out light. A single quasar can outshine an entire galaxy of hundreds of billions of stars, which is exactly why one can be visible from more than 13 billion light-years away. We are not seeing the black hole itself, of course, because black holes emit no light. We are seeing the brilliant, tormented gas around it, screaming with radiation as it falls, and from the properties of that light we can work backward to weigh the darkness at the centre. That is how we know the mass. We measure how fast the gas is moving in the black hole's grip, and the speed tells us the strength of the gravity, and the gravity tells us the mass. 800 million suns. To feel that number, set it against something familiar. Our own galaxy has a supermassive black hole at its centre, and it holds about 4 million times the mass of the Sun. The black hole in this ancient quasar is roughly 200 times heavier than that, and it had reached that size when the universe was less than 1/20th of its current age. Our galaxy's central black hole has had the full 13.8 billion years to grow to 4 million solar masses. This one reached 800 million in under 700 million years. The comparison is almost unfair. It is as if you looked away from a newborn for a moment and turned back to find it fully grown and towering over you. The mystery of these early giants has only sharpened in recent years. The James Webb Space Telescope, peering into the young universe with more sensitivity than anything before it, has been finding a population of small, red, compact objects in the early cosmos, and many of them appear to host black holes that seem too massive for their surroundings and their age. Whatever was building heavy black holes early was not a one-off accident that made a single freak quasar. It seems to have been a general feature of the young universe, a widespread process we do not fully understand, planting heavy seeds again and again in an era we can barely observe. The single strange object has become a pattern, and a pattern is much harder to wave away than a fluke. There are people who take all of this and conclude that the Big Bang model must simply be wrong, that objects too big too early prove the whole framework is broken. But that is not what the science says, and it is worth being careful here. These giants are not evidence against the early universe. They are evidence that something in our account of how black holes are seeded is incomplete. The Big Bang framework is what let us calculate that they should not fit in the first place, and the framework is what is guiding the search for the heavy seeds that would explain them. The honest position is not that the beginning is a lie, but that the first few 100 million years hold a process we have not yet named, working in a chapter we cannot yet read. I find this one quietly haunting, and I want to tell you why. Methuselah could be explained away as a clock that runs slow. This cannot. The object is exactly what it looks like, and it is exactly what our theory says should not exist yet. When you look at J1342 plus 0928, you are looking at proof that the universe's most powerful engines were already running before we can see anything at all, and that the machinery to build them was assembled in a chapter that is closed to us. Behind our earliest view, in the part of the story before the first light broke through, something was working fast and working large. We can only stand at the edge of that darkness and read its handwriting in the monsters it produced. And that is a strange kind of oldness. Not older than the universe, but older than our sight of it. The next object goes one step further because it may carry the fingerprint of something that was here before our universe began at all. Part 3. The bruise in the first light. To find the next object, we have to look at the oldest light there is, and then find the one place where that light is wrong. When we look out far enough in every direction, past the galaxies and past the quasars, we eventually reach a wall of light that fills the entire sky. This is the cosmic microwave background, the leftover glow from when the universe was about 380,000 years old, the moment it first cooled enough to become transparent and let light travel freely. It is the earliest picture we have, a baby photograph of the whole cosmos, and one of its most important features is how astonishingly smooth it is. Wherever you look, the temperature of that ancient glow is very nearly the same, varying by only tiny fractions, the faint density ripples that would one day grow into galaxies. It is smooth almost everywhere. Almost. In 2004, researchers studying data from a NASA satellite called the Wilkinson Microwave Anisotropy Probe found a place where the smoothness broke. In the direction of the constellation Eridanus, There is a region of that ancient light that is noticeably colder than everything around it, and it is enormous, spanning something like 1.8 billion light-years across the sky. They called it the cold spot, and more than 20 years later, no standard model of the universe has fully explained why it is there. You have to understand how unusual it is for the background light to have a feature like this. The tiny temperature variations in that glow are supposed to follow a predictable statistical pattern, the way grains of sand on a beach follow the predictable rules of wind and water. Small variations are common, a little warmer here, a little cooler there, but the cold spot is not a little cooler. It is a large, coherent, unusually cold region, far too big and far too cold to fit comfortably into the expected spread of random fluctuations. When cosmologists work out the odds of a feature like this appearing simply by chance in the standard picture, they get a probability of less than 2%. Not impossible, but unlikely enough to keep tugging at the sleeve of anyone who looks at it closely. For years, people have tried to explain the cold spot with things safely inside our own universe. The leading conservative idea is a supervoid, an unusually empty stretch of space between us and that patch of ancient light. Light passing through a very large void can lose a little energy along the way, arriving slightly cooler, and if the void were large enough it might account for at least part of the chill. That is the calm explanation, the one that keeps everything tidy. The trouble is that the supervoid, when people have gone looking for it, has not turned out to be quite large enough or quite empty enough to do the whole job on its own. And the other calm explanation, that it is simply a rare statistical fluke, is the kind of answer that never fully satisfies, because you can invoke chance to explain anything if you are willing to be lucky enough. And then there is the explanation that is not calm at all. In 2007, the physicist Laura Massini-Houghton proposed something that sounds like it belongs in a stranger kind of story, except that it comes wrapped in real mathematics. She suggested that the cold spot might be a bruise, not from anything inside our universe, but from another universe entirely pressing against ours. In this picture, our cosmos was not the only one. Before our universe went through its great early expansion, it existed as one possibility among many, one quantum fluctuation in a much larger structure that we would call a multiverse. And in that crowded early condition, a neighbouring universe could have pressed against ours, its gravity reaching across the boundary and leaving a mark on our primordial matter, a cold dent that has persisted in the background light for 13.8 billion years. Sit with what that would mean, if it were true. It would mean that the oldest light we can detect, the baby photograph of our entire cosmos, carries a mark that was pressed into it from the outside. It would mean that before our universe was fully itself, something else was already there, close enough to touch, close enough to leave a fingerprint. The cold spot would not merely be old. It would be a scar from before the beginning, a place where the boundary we call the start of everything was being leaned on from the other side. What draws physicists to the other universe idea, despite how outlandish it sounds, is that it did not arrive as an empty story. It came attached to a framework that made specific claims about what the ancient light should look like if our universe really had neighbours in an early crowded condition. That is the mark of a real scientific idea rather than a fantasy, that it sticks its neck out and says, if this is true, then you should find such and such in the data. The cold spot is one of the places people go looking to test that neck. It may not survive the testing. Extraordinary claims of this kind demand a mountain of evidence before anyone should accept them, and that mountain does not yet exist. But the idea is not idle speculation dressed up in equations. It is a genuine, if bold, attempt to explain a genuine, if faint, anomaly, and it makes predictions we can in principle check. I want to be very careful here, the way this channel is always careful, because it would be easy to run away with this. The multiverse bruise idea is one hypothesis among several, and it is not confirmed, and it may well be wrong. There are people who find it far too speculative, and their caution is reasonable. But I also want to be honest about the alternatives, because that is where the real strangeness lives. If you reject the other universe explanation, you are left with a super void that struggles to be big enough, or a random fluke sitting at the unlikely edge of the odds. None of the explanations are comfortable. Every road out of the cold spot leads somewhere that unsettles the tidy picture, and that is a pattern you're going to see again and again tonight. The grounded, careful, mainstream reading is not the safe one. It is often the one that leaves the deepest chill. To appreciate why any mark in this light matters so much, You have to understand what the cosmic microwave background actually is to us. It is the single most detailed and important measurement in all of cosmology, the source of much of what we claim to know about the universe, including its age and its composition. When we say the universe is 13.8 billion years old, that number comes in large part from reading the fine pattern in this ancient light. So the background is not just an old photograph. It is the foundation document, the primary source from which the rest of the story is reconstructed. And that is exactly why a feature we cannot explain in that light is so uncomfortable. It is a smudge on the founding document, a place where the most important data we have does something the model did not predict. The satellite that first spotted the cold spot, the Wilkinson Microwave Anisotropy Probe, mapped the whole sky in this ancient glow with more precision than anything before it, and a later mission, the Planck satellite, mapped it again with even sharper eyes. The cold spot survived both. It did not vanish when we looked harder, which is one reason it has stayed on the table for so long. Features that are merely mistakes tend to evaporate under better instruments. This one held. Whatever it is really there in the light, not an artifact of a single telescope having a bad day, and that persistence is what keeps drawing careful people back to it, turning it over, unable to quite explain it, and unable to quite dismiss it. It is worth understanding how you even measure something like the odds of the cold spot, because the statistics are the whole reason it refuses to go away. When cosmologists model the microwave background, they can generate enormous numbers of simulated universes, each with random fluctuations following the expected rules, and then go looking for how often a feature as cold and as large as the real cold spot shows up by pure chance. The answer that keeps coming back is that it is rare, appearing by chance in fewer than about 2 in 100 simulated skies. Now, 2% is not nothing. Rare things do happen, and if you look across a whole sky, you give yourself many chances to find something unusual. A careful skeptic can reasonably say the cold spot is simply the unlucky roll we happen to get. But 2% is also low enough that it keeps drawing serious people back to the data, unwilling to file it away as settled. The most studied ordinary explanation involves what happens to light when it crosses a great emptiness. As light from the ancient background travels toward us across billions of years, it passes through regions of varying density, and in an accelerating universe, a photon crossing an unusually large empty void can arrive slightly cooler than it started. So if there were a truly enormous supervoid sitting between us and that patch of the sky, it could chill the light passing through and produce something like a cold spot. Astronomers went looking for exactly such a void in the direction of Eridanus, and they did find an underdense region there. But when they measured it carefully, it did not seem large enough or empty enough to account for the full depth and size of the cold spot on its own. It might contribute. It does not obviously close the case. There is also a broader context worth mentioning, because the cold spot is not the only oddity in the ancient light. Over the years, cosmologists have flagged a handful of large-scale features in the microwave background that seem mildly surprising. Patterns and alignments that some have nicknamed with dramatic names, and that others insist are just the ordinary quirks of looking at a single sky, with human eyes hungry for patterns. The cold spot is the most robust and most discussed of these, the one that has survived the most scrutiny. Whether it is a genuine signpost pointing at something profound, or simply the most memorable face we have found in the cosmic clouds is still, honestly, an open question. And that honesty is the point. We are looking at the oldest light there is, and we have found a mark in it that we cannot fully explain, and every explanation we reach for from a void that is not quite big enough to a fingerprint from another cosmos leaves us less settled than before. Here is the human weight of the cold spot, the thing to carry with you as we go further down the list. We would like to believe that our universe began cleanly, sealed, alone, a single event with nothing before it and nothing beside it. The cold spot is one small, cold piece of evidence that this belief might be too simple. Whether it is a void, a fluke, or a fingerprint from another cosmos, it is a place where our clean story of the beginning develops a blemish we cannot rub out. And the next objects on this list will stop merely blemishing the beginning. They will start reaching back into the first second of it, to things that were already ancient when the light of the cold spot was still young. Part 4. The Holes Older Than Stars. So far, every object we have looked at is made of ordinary things behaving in extraordinary ways. A star burning its slow chemistry, a black hole feeding on gas, a cold patch in ancient light. But the next entry is different, because it belongs to a category of object that needs no stars, no galaxies, and no ordinary matter to form. It could have appeared in the first fraction of the first second, when there was nothing yet to make anything out of. These are the primordial black holes, and they predate almost everything you have ever been told is old. The idea comes from Stephen Hawking, who proposed it in 1971, years before he became a household name. Ordinary black holes, the ones we usually talk about, form when a massive star runs out of fuel and collapses under its own weight. That process requires a star, and a star requires time to form and time to die, which means ordinary black holes are, in the grand scheme, latecomers. Hawking asked a different question. What if you did not need a star at all? What if, in the wild, dense, chaotic conditions of the newborn universe, gravity could make a black hole directly, out of the raw texture of space itself? In the first tiny fraction of a second after the Big Bang, the universe was denser and hotter than anything that has existed since. It was not smooth. It churned with fluctuations, ripples in the density of matter and energy, some regions a little thicker than others, and Hawking realized that if a region were dense enough, if the fluctuation were sharp enough, gravity could win instantly. That pocket of extreme density could collapse on the spot into a black hole without ever passing through a star, without waiting for anything to be born. These black holes would not be the corpses of stars. They would be the firstborn, formed before the first star ever shone, forged out of the primordial chaos in the opening instant of time. What makes primordial black holes so strange is the range of sizes they could come in. Because they form from fluctuations rather than from stars, they are not tied to the usual stellar masses. Some could be tiny, no larger across than an atom, and yet weigh as much as a mountain, a whole mountain's worth of mass squeezed into a speck. Others could be far larger, rivaling the mass of stars or exceeding them. There is no single expected size, only a spectrum stretching across a range so wide it is difficult to picture, from the atomic to the astronomical, all of them born in the same instant, all of them older than the first light. And here is where this entry earns its place further down the list than the ones before it, because primordial black holes may reach back even earlier than the first fraction of a second we can describe. Some models suggest that the density fluctuations that made them did not arise in the ordinary early universe at all, but before the inflationary epoch, before the burst of exponential expansion that shaped everything we can now observe. If certain conditions existed before inflation, and if those conditions created regions of extreme density, then those regions could have collapsed into black holes before the universe had even finished deciding what its own fundamental structure would be. Picture that carefully. A black hole formed in a proto-universe, in the moments before our cosmos settled into the physics we recognize, and then carried through inflation and through the entire 13.8 billion years that followed, surviving all of it, drifting silently forward into the present. An object older than the rules that govern the space it moves through. There is one more turn to this, and it may be the most unsettling of all. For decades, cosmologists have been trying to explain dark matter, the invisible substance that makes up roughly 27% of everything, the unseen mass whose gravity holds galaxies together and bends the paths of stars. We know it is there because we can feel its pull. We have never seen what it is made of, and one of the serious candidates, one of the real proposals on the table, is that some portion of dark matter might be primordial black holes. The invisible scaffolding of the cosmos, the framework that keeps galaxies from flying apart, might be built in part out of these ancient firstborn holes set in place before galaxies, before stars, before atoms themselves. Let that settle. If it is true, even partly true, then the structure of everything you can see is hanging on anchors that were forged before there was matter as we understand it. The bright spiral of a galaxy, the slow wheeling of its stars, all of it organized around gravity from objects that predate the first atom. We would be living inside a cosmos whose bones are older than its flesh, whose skeleton was set before the body existed, and those bones would be invisible, drifting through the space around us, silent and dark and unimaginably old. What I find most disorienting about primordial black holes is that they invert the usual order of creation. In the story we normally tell, first came the simple things, and then the complex ones. First the particles, then the atoms, then the stars, and only much later, after stars had lived and died, the black holes that are their corpses. Black holes, in that telling, are an ending. the last chapter of a massive star's life. But primordial black holes would be a beginning. They would come first, before the atoms, before the stars, formed directly out of the raw density of the newborn universe. That means the objects we usually think of as the final graves of stars could, in one form, be older than stars themselves, older than the first atom, present at the very opening of the cosmic story rather than its close. The tombstone, in this case, would predate everything it was supposed to commemorate, and because they form from fluctuations rather than from stars, they answer to no minimum size. Every black hole we have ever confirmed came from a dying star or from the mergers and growth that followed, and that history sets a floor on how small they can be. Primordial black holes have no such floor. They could be enormous, or they could be tiny beyond ordinary imagining, and the whole spectrum could exist at once, all of them stamped out in the same first instant. That freedom is what makes them such a flexible idea, able to hide in so many corners of the universe, and also what makes them so hard to pin down. We are not looking for one kind of object. We are looking for a whole family of them, born together at the beginning, scattered across every possible scale. There is a beautiful and unsettling consequence of Hawking's idea that deserves its own moment, because it turns these ancient objects into a kind of cosmic clock. Hawking is famous for showing that black holes are not entirely black, that they slowly leak energy and shrink over enormous spans of time, a process we now call Hawking radiation. Big black holes leak so slowly that they will effectively last forever. But very small black holes leak quickly, and the smallest ones would radiate themselves away entirely in far less than the age of the universe. This gives us a strange kind of leverage. If primordial black holes below a certain tiny size had formed, they would already have evaporated by now, and in their final moments they would have released a burst of energy we might be able to detect. We look for those bursts, we have not clearly found them, and that absence quietly tells us something about what the first instant did and did not make, ruling out certain sizes and leaving others open. The dark matter connection deserves a moment on its own, because it is the twist that turns these ancient objects from a curiosity into a possible foundation of everything. For decades we have known that galaxies contain far more gravity than their visible matter can account for. Stars at the edges of galaxies orbit far too fast for the stars and gas we can see to hold them in place, and galaxies within clusters move as though gripped by unseen mass. Something invisible is out there, roughly 5 times as much of it as all the ordinary matter combined, and we do not know what it is. Most candidates involve some new, undiscovered particle, but primordial black holes offer a very different kind of answer, one that requires no new particle at all, only that the first instant made enough of these ancient holes in the right range of sizes. On that picture, the unseen mass shaping every galaxy would be built from objects older than the galaxies themselves. Dark, not because they are made of something exotic, but because they are black holes, and black holes give off no light. Whether or not that turns out to be the answer, simply holding the possibility in mind changes the character of the dark around us. We are used to thinking of empty space as empty, and of the invisible mass in galaxies as some faint diffuse substance. But if even a fraction of it is primordial black holes, then the framework holding the galaxies together is made of discrete ancient objects, each one a sealed remnant of the opening instant, drifting silently through and around every galaxy including our own. The scaffolding would not be a mist. It would be a population, uncountable and unseen, older than the first star, holding the bright wheels of the galaxies in place from the shadows. The sizes that remain open are what keep the dark matter possibility alive. There are windows in the range of possible masses where primordial black holes have not been ruled out, where they could still be drifting through the cosmos in enough numbers to account for some or all of the unseen mass. Astronomers hunt for them in clever ways. One method watches distant stars for a telltale flicker, because if a dark, massive object passes between us and a background star, its gravity can briefly bend and brighten that star's light, a momentary flare with no visible cause. Campaigns watching millions of stars for exactly this kind of flicker have placed limits on how many such objects can be out there, narrowing the windows without closing them entirely. The search continues, patient and painstaking, looking for the fingerprints of objects that give off no light of their own. Interest in these ancient holes surged again after the gravitational wave detectors began catching black holes colliding, some of them with masses that were a little surprising, a little harder to explain through ordinary stellar deaths. It made people wonder, out loud and in the literature, whether at least some of the black holes we are now hearing collide might not be the corpses of stars at all, but firstborn holes from the opening instant, finally meeting after 13 billion years of drifting. We do not know. It may be an ordinary explanation. But the question itself is remarkable, that we could be listening right now to the collisions of objects older than the first star. To hold the scale of these things in your mind, return to the smallest ones for a moment. Picture a black hole no larger across than a single atom, and yet holding the mass of an entire mountain, a mountain's worth of matter crushed into a point too small to see. It would drift through ordinary matter almost without effect, a speck of concentrated gravity, silent and ancient, older than atoms, possibly older than the physics that governs the space it moves through. There could be many of them, or few, or none. We are still learning to look, but the mere possibility reshapes the emptiness. The dark between the stars may not be empty at all. It may be threaded with the oldest, densest, most invisible objects the universe ever made. I want you to notice how far we have already travelled from where we began. We started with a single faint star whose age might just be a measurement error. Now we're talking about objects that may have formed before the universe finished becoming itself, objects that may be the very thing holding the galaxies together, objects we cannot see and have never touched. The oldest things, it turns out, may also be the most invisible. They do not announce themselves, they do not shine, they simply hold, quietly, from a time before time was properly running. How many of these ancient gravitational seeds are drifting through our own galaxy right now, dark and silent, older than every star around them? We do not know. We're still learning how to look for something that gives off no light and reveals itself only through its pull. But the possibility alone reshapes the way you look at the night sky. The bright things you can see may be the young things. The old things may be the ones you cannot see at all, holding everything in place from the shadows of the first instant. And the next object is older still, not a hole in space, but the very stuff that space was waiting to become. To find it, we have to travel into a darkness so complete that no star had ever shone. Part 5. The Long Dark Before the First Star. We tend to imagine the early universe as a place of fire and light, a brilliant explosion, a blaze of newborn energy. But there was a chapter, and a long one, when the universe was not bright at all. There was a chapter when it was utterly, completely dark, and it lasted far longer than you would ever guess. This is the era astronomers call the Cosmic Dark Ages, and the objects that filled it are the next entry on our list, because they are the raw material of everything, and they existed before the first point of starlight was ever struck. In 2011, astronomers using the Atacama Large Millimeter and Submillimeter Array in Chile, an enormous grid of radio dishes on a high desert plateau, detected molecular clouds at extreme distances, so far away that we were seeing them as they were within the first few 100 million years after the Big Bang. These clouds were made almost entirely of hydrogen and helium, the two lightest elements, the ones forged in the first minutes of the universe. They were the raw stock from which the first stars would eventually be built. But here is the point that matters for tonight. The clouds came first. They predate the stars they would give birth to by tens of millions of years. They were already there, drifting before a single star existed to light them. To understand what these clouds are, you have to understand the timeline they belong to. After the Big Bang, the universe was a blazing plasma, too hot for atoms to hold together. Then, about 380,000 years in, it cooled enough for the first atoms to form, and the light that had been trapped in the plasma was suddenly free to travel. That released light is the cosmic microwave background we spoke of earlier, the oldest light there is. But once that light was set free and stretched out by the expanding universe, something strange happened. The universe went dark. The first atoms had formed, but no stars had yet ignited to make new light. And so, for a period lasting roughly 100 to 200 million years, the cosmos contained no luminous objects at all. No stars, no galaxies, no light of any kind, anywhere. Try to picture the scale of that. For a stretch of time longer than the entire age of the dinosaurs on Earth, the universe was a lightless place. The only things in it were these enormous cold clouds of hydrogen and helium, drifting through absolute blackness, slowly gathering under their own gravity, waiting. There was nothing to see, because there was nothing giving off light to see by. There was no colour. There was no shadow, because shadow requires light to block. There was only cold gas in the dark, patient beyond any patience we can imagine. holding within it the entire future of everything. Let me take you into that darkness for a moment, because I think you have to feel it to understand it. Imagine you are there somehow, floating in the universe during the Dark Ages. You open your eyes, and there is nothing. Not the darkness of a room at night, where your eyes eventually adjust and find some faint edge to hold on to. This is a darkness with no edges at all, because there is not a single source of light in all of existence to adjust to. You reach out and there is cold, thin gas around you, hydrogen and helium, so sparse you would barely feel it, drifting slowly in currents you cannot see. There is no sound, there is no warmth. There is only the gas and the dark and the slow, silent pull of gravity, gathering the gas into knots over spans of millions of years. And then, somewhere far off, in one of those knots, the gas grows so dense and so hot at its core that it crosses a threshold, and for the first time in the history of the universe, a star ignites. One point of light, in a darkness that had held for 200 million years, the first dawn, and everything that would ever come, every galaxy, every world, every living eye that would one day look up, began in that transition from the long dark to the first light. The chemistry inside those clouds reaches back even further than their formation, and this is the detail I find most quietly astonishing. The exact ratio of hydrogen to helium inside them, roughly 3 parts hydrogen to 1 part helium by mass, was not set when the clouds formed. It was set in the first 3 minutes after the Big Bang, during the brief window when the universe was hot enough to forge atomic nuclei, a process called Big Bang nucleosynthesis. That ratio was locked in when the universe was minutes old, and then it sat, unchanged, inside these clouds, for hundreds of millions of years of darkness. So when we study a primordial molecular cloud, we are not just looking at an old object. We are looking at a container of primordial chemistry, a sealed jar holding the exact conditions of the universe's first 3 minutes, preserved through the entire long dark. It is worth dwelling on how strange this era is compared to the universe we take for granted. We are used to a cosmos defined by its lights, a sky full of stars, a night sky that is really a catalogue of distant fires. But for the whole span of the Dark Ages, that catalogue was empty. There was matter, and there was space, and there was the slow, patient pull of gravity, but there was no fire anywhere to see any of it by. The universe existed fully, and yet it was invisible to itself, because nothing in it was shining. If you had been there, you would not have been in a dim place. You would have been in a place with no light source at all, a completeness of dark that has never existed since. Because ever since the first star ignited, there has always been light somewhere, and the darkness was not brief. Set it against the timescales you know, the dinosaurs ruled the Earth for something on the order of 150 million years, and spans so long it strains the imagination. The Dark Ages lasted comparably long, 100 to 200 million years of a lightless cosmos, gas gathering in the black, gravity doing its slow and silent work. Nothing hurried, nothing shone, and through that entire immense stretch, the clouds simply drifted and gathered, holding their primordial chemistry, waiting for the density in some knot somewhere to finally cross the threshold and light the first fire. When we call these clouds ancient, that is the age we mean. They are older than the first light, and they held their vigil in the dark for longer than many of the great chapters of Earth's own history. One of the most remarkable things happening in astronomy right now is that we are learning to hear the Dark Ages, even though there was no light in them to see. The trick is a particular signal given off by neutral hydrogen, a faint radio whisper produced by hydrogen atoms across the young universe. As that whisper travelled toward us across billions of years, it stretched to longer and longer wavelengths, and by measuring it, we can, in principle, take the temperature of the gas during the long dark, before any star had formed. In 2018, one experiment reported a tentative detection of just such a signal from the era of the very first stars, hinting at the moment the dark began to end. The result is still debated, still being checked, because a whisper that faint is extraordinarily hard to separate from the noise of our own galaxy and our own instruments. But the ambition of it is staggering. We are trying to listen to a universe that had no light, to read the story of the dark from the faint radio breath of the gas that filled it. The mechanism that ended the Dark Ages was gravity, working with a patience that has no human equivalent. In the beginning, the gas was almost perfectly smooth, but not quite, carrying those faint density ripples we can still read in the ancient light. Wherever the gas was very slightly denser than average, its gravity pulled a little harder, drawing in more gas, which made it denser still, which pulled harder yet. Over tens of millions of years, this slow feedback gathered the thin gas into ever tighter knots, and in the densest cores of those knots the gas grew hot enough at last to ignite fusion. That was the first light. But every step of that assembly, all those long millions of years of gathering, happened in total darkness, guided by nothing but gravity acting on cold gas. The clouds were not passive during the Dark Ages. They were slowly becoming the engines of the first dawn, in a blackness with no witness. The end of the Dark Ages, when it finally came, was one of the most important transitions in the history of everything. The first stars to form were unlike any star that exists today, made purely of hydrogen and helium. With none of the heavier elements that stars now contain, they could grow to enormous sizes, blazing hot and blue and short-lived, burning fiercely and dying young. And when they died, in tremendous explosions, they forged and scattered the first heavier elements, the first carbon, the first oxygen, the first iron, seeding the gas around them so that the next generation of stars and eventually planets, and eventually us, could be made of something more than the two lightest elements. Everything heavier than helium in your body was made in a star that formed after the Dark Ages ended. But the clouds themselves, the raw hydrogen and helium, came before all of that, waiting in the dark for the fire to begin. The James Webb Space Telescope is now pushing our view closer and closer to that first dawn, catching the light of some of the earliest galaxies, seeing the universe as it was when the first stars were igniting and the dark was breaking. Each new observation reaches a little further back toward the edge of the long night, and what makes this era so haunting is that it sits right at the boundary of what we can ever see. The molecular clouds of the Dark Ages gave off no light of their own. They can be studied only in indirect ways, through the faint radio whisper of their hydrogen, through the shadows they cast, through the material they would become. They are almost, but not quite, beyond our reach, precursors sitting just on the far side of the first light. Here is the human weight of these clouds, and it is a strange and tender one. Every star that has ever burned was made from clouds like these. Every planet, every atom of carbon in your body, every molecule of water you have ever drunk, all of it traces back to hydrogen and helium that drifted in absolute darkness for hundreds of millions of years before the first light was ever struck. You are quite literally made of things that spent the infancy of the universe in the dark. The raw material of you existed as formless, lightless gas, patient in a cosmos with no stars, waiting for a dawn that had not yet come. These clouds are not objects within the universe as we know it. They are the precursors to it, the ingredients laid out before the recipe was cooked. And they raise a question that has no comfortable answer. If the building blocks of everything sat in formless darkness for so long, what finally reached in and lit the first fire? What ended the long dark? We are still not entirely sure. And the next object is older than the clouds, older than the Dark Ages, a relic not of the first 100 million years but of the first single second, and it is not somewhere far away. It is inside you right now. Part 6. The oldest thing inside you. Everything we have looked at so far, you have had to imagine at distance. A star in Libra, a quasar across 13 billion years, a cold patch in the ancient sky, clouds in the long dark, all of it far away, all of it out there. But the next object on the list is not out there. It is here. It is passing through your body as you listen, in numbers so large they defy counting, and it is older than every atom you're made of. To meet it, you do not have to look up. You only have to realize what is already moving through you. In the 1960s, physicists working out the consequences of the Big Bang predicted that there should be a kind of relic radiation, even older than the cosmic microwave background. Remember, the microwave background is the light released when the universe was about 380,000 years old. That is old, unimaginably old. But this prediction reached back much further, to about 1 second after the Big Bang, and the messengers it predicted were not particles of light. They were neutrinos, the faintest, most ghostly particles we know of, and the relic they form is called the cosmic neutrino background. To understand why these neutrinos are so old, you have to understand what the universe was like 1 second in. It was a furnace beyond any furnace, a superheated plasma of fundamental particles at temperatures above 10 billion degrees. Protons and neutrons had not yet assembled into the nuclei of hydrogen and helium. There was no chemistry. There was no structure of any kind larger than a single particle. Everything was packed together so tightly and so violently that all the particles were constantly slamming into one another, unable to travel freely. But neutrinos interact with matter so weakly, so reluctantly, that at about 1 second in, as the universe expanded and thinned, they simply stopped colliding with everything else and began to stream freely through space. They decoupled. They broke away from the furnace and started flying, and they have been flying ever since for 13.8 billion years, carrying with them the imprint of a moment when the universe was 1 second old. Now here is the part that should make you sit up, even as you are lying down. These relic neutrinos are not rare and they are not distant. Space is filled with them. In every single cubic centimetre of space, right now, there are roughly 330 of these neutrinos, left over from the first second of existence. Every cubic centimetre, including the cubic centimetres occupied by your own body, which means that trillions of these particles are passing through you every second, streaming through your hands, through your chest, through the space behind your eyes, each one a fossil from the first second of the universe, each one older than the atoms that make up your flesh and bone. Let me slow this down because I want you to really be here for it. Right now, as you lie in the dark, your body's being passed through, continuously and silently, by particles that were set free when the universe was 1 second old. They do not touch you in any way you can feel. They do not warm you or push you or leave any trace. They pass through your body the way light passes through glass, as if you were not there at all, and then they continue on into the space beyond you, and then out past the planet and onward. Trillions of them, every second, older than every star, older than every atom, older than matter itself in any form you would recognize. The single oldest thing you will ever be in contact with is not in a museum and not in a distant galaxy. It is inside you, right now, moving through you as you drift towards sleep, and you cannot feel a single one of them. And here is the strangest twist of all. We have never directly detected these neutrinos. We are certain they exist, because the physics of the Big Bang requires them, and everything else about that physics has held up. But catching one has proven almost impossible. Over the billions of years since they broke free, they have cooled along with the expanding universe, down to a temperature of about 1.95 degrees above absolute zero, barely a whisper of energy above the coldest possible cold. At that temperature, they are so faint, so low in energy, that our most sensitive instruments cannot yet register them. So we are in the peculiar position of being surrounded by the oldest particles in existence, bathed in them, passed through by them constantly, and still unable to hold up a detector and say, "There, I have caught one." They are everywhere and untouchable at once. There is a comparison worth making because it puts the age of these particles in order against the other relics we can gather. Think of the great messengers that reach us from the past. Ordinary starlight brings us news from thousands or millions of years ago, which is old by any human measure. The cosmic microwave background brings us the universe as it was at 380,000 years, far older still, the oldest light there is. But the neutrino background reaches back further than any of these to 1 second. Compared to 380,000 years, 1 second is almost the very edge of the beginning. These particles carry the imprint of a universe that had not yet made a single atomic nucleus, a universe still too hot and too violent for even the simplest structure to hold together. Of everything we can hope to gather from the past, the relic neutrinos are the most ancient sea, and they are the sea we are swimming in, and the number bears repeating slowly, because it is easy to hear it once and not feel it. Roughly 330 of these relic neutrinos sit in every cubic centimetre of space. A cubic centimetre is about the size of the tip of your finger. So in a volume no bigger than a fingertip, at every point in the room around you, and in the space your own body occupies, there are hundreds of these fossils from the first second, and they are not sitting still. They are streaming through at enormous speed. Multiply that fingertip volume up to the size of your whole body, and the count runs into the trillions passing through you each second, a constant silent flood of the oldest particles in existence, pouring through you as though you were made of open air, which, to a neutrino, you very nearly are. It helps to understand what neutrinos actually are, because their strangeness is the whole reason they can be this old and this near at the same time. Neutrinos are among the most abundant particles in the universe, and also the most reclusive. They carry almost no mass, no electric charge, and they interact with ordinary matter so feebly that they pass through it as if it were not there. To give you a sense of just how reluctant they are, a neutrino could pass through a wall of solid lead many light years thick and still have a good chance of coming out the other side without touching anything. They are produced in enormous numbers by the sun, by nuclear reactors, by exploding stars, and they stream through the entire Earth constantly, day and night, from above during the day and up through the ground beneath you at night, because the planet is simply no obstacle to them. This reclusiveness is exactly why the relic neutrinos from the first second are still here, unabsorbed, undisturbed, having sailed through everything for 13.8 billion years. The relic neutrinos are older and colder than the light of the cosmic microwave background, and that ordering matters. The microwave background comes from 380,000 years in. The neutrino background comes from about 1 second in. So of the two great relics that fill all of space, the neutrino sea is by far the more ancient, a snapshot of the universe from a time when it was still a furnace of raw particles, before even the simplest atomic nuclei had assembled. And because the universe has expanded and cooled so enormously since then, these neutrinos have been stretched down to an almost unimaginable gentleness, cooled to about 1.95 degrees above absolute zero, even colder than the microwave background's faint warmth. That extreme coldness is precisely what makes them so nearly impossible to catch. Think about what a single one of these particles has been through, and has not been through. It was set free when the universe was 1 second old, in a furnace above 10 billion degrees, and since that moment it has simply travelled, in a straight line, for 13.8 billion years, almost never interacting with anything at all. It did not pass through the forming of atoms because it had already left. It watched, in a sense, from the outside, as the universe cooled, as the first atoms assembled, as the long dark settled in, as the first stars ignited and galaxies wheeled into being, and it took no part in any of it, touching nothing, changing nothing, changed by nothing. It has carried the imprint of that first second, unaltered, across the entire history of the cosmos, and it is carrying it still, right now, as it slips through you. It is a perfect messenger precisely because it is such a poor participant, so reluctant to interact that it preserved its ancient news intact all the way to the present. There are physicists trying to catch them anyway, and the attempt is one of the most audacious experiments ever conceived. The idea is to build a target so sensitive that one of these ghostly relics might very rarely deposit a tiny signal, a faint kick that our instruments could register against the noise. The engineering challenge is immense, because the signal we are looking for sits right at the edge of what any detector can distinguish from nothing at all. But if it ever succeeds, if we ever directly catch a relic neutrino from the first second, we will have reached out and touched a fossil from the opening moment of the universe, a particle that has been flying since before atoms existed. We would be holding for an instant the oldest thing anyone has ever measured. There is a kind of vertigo in that, and it is the intimate kind rather than the cosmic kind. We are used to the oldest things being the most remote, the things you need a telescope and a lifetime to reach. But the cosmic neutrino background flips that around. The oldest thing is the nearest thing. It is not out at the edge of the observable universe. It is in the room with you, in the bed with you, in your body, threading through you in uncountable numbers, a constant quiet rain of relics from the universe's first second. You have been swimming in the oldest sea there is your entire life and never felt the water. What information about the first second is written into these ancient particles, waiting for us to finally learn how to read it? And if we struggle even to detect the relics of 1 second in, what might be hiding even earlier, before that first second, in the part of the story governed by physics we have not yet written? These are the questions the neutrino background leaves drifting through you. And from here, the list stops being about particles and objects at all, and starts being about patterns, about structures written into the universe before matter had cooled enough to form a single atom. The next entry is not a thing you could hold. It is a shape, printed across the whole sky, and it decided where the galaxies would go. Part 7. The sound that built the sky. The next object on our list is not an object in the way the others have been. You could not point a telescope at it and see a shape. You could not hold it, or drift through it, or be passed through by it, and yet it is printed across the entire universe, a pattern hundreds of millions of light-years wide, repeated everywhere you look, and it was set in motion by sound waves that rang out before the first atom ever formed. It decided in part where the galaxies would sit. It is called baryon acoustic oscillations, and once you understand it, you will never look at the arrangement of the night sky the same way again. Let me start with the strange, almost musical fact at the centre of this. The early universe had sound in it, real sound, real pressure waves, moving through the primordial plasma the way sound moves through air. Before the universe cooled enough for atoms to form, it was a hot, dense soup of particles and radiation, and that soup could carry waves. Gravity pulled matter inward, trying to clump it together. Radiation pushed outward, resisting the clumping, and this tug of war, this endless push and pull between gravity pulling in and pressure pushing out, sent waves rippling through the plasma, spheres of compression spreading outward from every dense point, like the ring that spreads when you drop a stone into still water, except in 3 dimensions and everywhere at once. These pressure waves travelled fast at something like half the speed of light, spreading outward through the young universe for about 380,000 years, and then something happened that froze them in place. At about 380,000 years, the universe cooled enough for the plasma to become neutral atoms. The radiation that had been pushing outward suddenly decoupled from the matter and streamed away as light, the very light we now see as the cosmic microwave background, and without that outward pressure the waves stopped. Each expanding sphere of sound froze exactly where it was, leaving a shell of slightly denser matter at a fixed distance from every original starting point. The music stopped, and the last note was left standing in the matter of the universe. Now think about what that frozen shell would do over the following billions of years. Matter is slightly more concentrated on that shell, which means gravity is slightly stronger there, which means galaxies are slightly more likely to form there. So the frozen sound wave became a faint preference written into where galaxies would eventually appear. Everywhere in the universe, there is a slightly higher chance of finding a galaxy at a specific distance from any other galaxy, and that distance is the size of the frozen sound shell, stretched out by billions of years of cosmic expansion. Today, that characteristic distance is about 490 million light-years. It is a ruler, a fixed length, printed into the large-scale structure of the cosmos by sound waves that fell silent when the universe was 380,000 years old. In 2005, the Sloan Digital Sky Survey, a massive effort to map the positions of enormous numbers of galaxies, confirmed that this pattern is really there. When astronomers measured the distances between enormous numbers of galaxies, they found the faint but unmistakable excess, the slight overabundance of galaxy pairs separated by that specific 490 million light-year scale. The frozen sound was real. The ruler was real. The music of the early universe had left a fingerprint on the arrangement of everything, and we had finally learned to read it. I want you to hold the full weight of what this means, because it is one of the most quietly staggering facts in all of cosmology. The positions of galaxy clusters, structures holding trillions of stars, were influenced by sound waves that rang through a formless plasma billions of years before those galaxies existed. The architecture of the universe, the grand pattern of where matter gathered and where it thinned, was substantially decided in the first 380,000 years. Everything that came afterward, every galaxy, every solar system, every planet capable of holding an ocean or a forest or a living thing, assembled at least partly according to a blueprint that was drawn before matter had cooled enough to form a single atom of hydrogen. There is a detail here that quietly overturns how most of us picture the early universe. We tend to imagine the young cosmos as chaos, a formless blaze with no order to it. But the plasma that filled it was not chaotic at all. It was a resonating medium, capable of carrying clean, organised waves, ringing like the air inside an instrument. When you pluck a guitar string or blow across the mouth of a bottle, you get a specific tone because the physical size of the thing selects certain wavelengths and rejects others. The early universe did something similar on the grandest scale. The competition between gravity and radiation pressure, playing out for exactly 380,000 years before the plasma froze into atoms, selected a characteristic wavelength, a preferred size for its waves. That is why the pattern in the galaxies has a specific scale rather than a smear of random ones. The universe had a note, a fundamental tone, set by its own physics and its own clock. And that note did not simply fade away when the music stopped. It was frozen into the matter and then carried forward, stretched larger and larger by the expansion of space over billions of years, until the original scale of the sound wave had grown to the 490 million light-years we measure between galaxies today. So when we map the galaxies and find that faint preferred spacing, we are not looking at something that merely resembles the old sound wave. We are looking at the very same wave, the actual frozen crest of a real oscillation, enlarged by cosmic expansion but unbroken, a physical object that has persisted from the first 380,000 years to now. The oldest note ever struck is still standing in the sky, only far larger than when it was played. What makes this frozen sound so useful, beyond its strangeness, is that it works as a ruler we can trust. Because the physics that set the scale of those sound waves is well understood, we know how large that frozen shell should be, and when we measure how large it appears at different distances across cosmic history, any difference between the true size and the apparent size tells us how much the universe has stretched in between. That turns baryon acoustic oscillations into one of the most precise tools we have for measuring the expansion of the cosmos and the mysterious dark energy that is driving that expansion faster and faster. A pattern printed by sound in the first 380,000 years has become the yardstick by which we measure the fate of everything. The oldest music in the universe is how we take the measure of its future. That work is very much alive right now. Enormous surveys are underway that map millions upon millions of galaxies specifically to trace this frozen sound across as much of cosmic history as possible, refining the ruler, pinning down how the expansion has changed over billions of years. Some of the most recent results have hinted tantalizingly that dark energy might not be perfectly constant, that its strength might shift over time, and if that holds up it would be a profound clue about the far future and the true nature of the cosmos. And the tool doing that work, the thing making those measurements possible, is the last note of a sound that stopped playing when the universe was a newborn. We are using the ringing of the first plasma to ask what will become of everything. I want to make sure the core image really lands, because it is easy to say sound in the early universe and let it slide past as a metaphor. It was not a metaphor. The early universe genuinely carried pressure waves, real oscillations of compression and rarefaction moving through the plasma, exactly the physical phenomenon that sound is. If you could somehow have been there, with some impossible ear, the young universe would have been humming, ringing with these waves at frequencies far too low for any ear to hear, a tone stretched across hundreds of thousands of years. Some researchers have even taken the measured pattern and shifted it up into the range of human hearing, so you can listen to a rough rendering of what the early universe sounded like. A low, rolling tone, the first and oldest music there was. And then that music stopped, and its final chord froze into the arrangement of the galaxies, and we live inside the last note to this day. Here is the thought I cannot shake, and I want to hand it to you carefully. Our galaxy sits where it sits. Our galactic neighbourhood is arranged the way it is arranged. And that arrangement, the very stage on which our entire existence plays out, was shaped in part by pressure waves that moved through a universe that bore no resemblance to the one we live in. There were no stars then. There were no atoms. There was only the hot plasma and its ringing. And yet the ringing reached forward across 13 billion years and helped decide where you would one day be. Not in a mystical sense, in a measurable physical sense. The room you were born into was laid out before there was matter to build rooms from. There is a further strangeness worth naming, because it deepens the sense of authorship. The pattern is not something you would ever notice by looking at any one patch of sky. If you pointed at two galaxies and asked whether they sit 490 million light-years apart, the answer would usually be no, because the preference is faint, a gentle statistical lean rather than a rigid grid. You can only see it when you map enormous numbers of galaxies at once and let the slight excess reveal itself in the crowd. In other words, the fingerprint is written across the whole population of the cosmos rather than stamped on any individual member of it. No single galaxy carries the mark. The mark lives in the arrangement of all of them together, a pattern that only exists at the scale of everything, and that pattern was set by the ringing of the first plasma, which means the universe as a whole remembers a sound that no single part of it could tell you about. I keep coming back to the word blueprint, because it is almost too apt. A blueprint is drawn before the building exists and it constrains, without fully determining what the building will become. That is exactly the role the frozen sound played. It did not force any particular galaxy to form in any particular spot. It gently tilted the odds everywhere at once toward a certain spacing, and then the universe spent billions of years filling in the details on top of that faint underlying plan. So the cosmos we see is neither purely random nor rigidly fixed. It is improvisation over a score, and the score was written in the first 380,000 years, in a language of pressure and sound, by a universe that had no stars, no atoms, and no idea what it was composing. That is the emotional weight of baryon acoustic oscillations, and it lands differently from the others. The neutrino background was old and near. The primordial black holes were old and invisible. But this is old and structural. This is the discovery that the shape of the cosmos, the framework that determined our address within it, was set by a sound that fell silent before the first atom formed. We think of our place in the universe as an accident, a contingency, something that just happened to work out this way. And baryon acoustic oscillations whisper back that some of it, at least, was decided in advance, printed into the fabric of things during the universe's first fraction of its first percent of its life. What does it mean that the cosmos we live in is arranged, even in part according to acoustic patterns from an era when nothing recognizable existed? And how much of what we consider contingent or accidental or random about our location was actually settled before atoms themselves had formed? These oscillations do not merely date back to the early universe. They are the structural foundation of the sky above you, the crystallized last note of a music that stopped playing when the universe was a newborn. And the next entry is fainter still, and reaches back further, into a framework that threads the emptier spaces between the galaxies, a structure that may predate even the inflation that shaped everything else. Part 8. The Web You Cannot See. If you could pull back far enough from the universe to see its largest structure all at once, you would not see galaxies scattered at random like grains of sand thrown across a floor. You would see a pattern. The galaxies gather along immense filaments, threads of matter stretching across hundreds of millions of light years, meeting at bright knots and clusters, with enormous empty spaces between them. Astronomers call this pattern the cosmic web, and it is the largest structure there is, and running through it, threading the filaments and reaching even into the emptiest voids, is something that should not be there at all. There are magnetic fields in the spaces between the galaxies, and their origin may reach back before the universe as we know it began. In 2010, observations from the Fermi Gamma Ray Space Telescope revealed evidence of magnetic fields permeating the enormous, nearly empty regions between galaxy clusters. This was a genuine surprise, and to understand why, you have to understand how we usually explain magnetic fields. On Earth, the magnetic field comes from the churning of molten metal in the planet's core. In stars, it comes from the swirling of hot plasma. In galaxies, it comes from the slow rotation and turbulence of gas over billions of years. In every familiar case, a magnetic field is generated by matter in motion, by something dense and dynamic doing work over time. But the spaces between galaxy clusters are the emptiest places in existence. There is almost no matter there. There is no churning core, no swirling plasma, no engine of any kind to generate a field. And yet the field is there. The strength of these intergalactic fields is almost unbelievably faint. We are talking about something on the order of a quadrillionth of the strength of Earth's magnetic field. A quadrillion is a 1 followed by 15 zeros, so imagine taking the modest magnetic field that turns a compass needle and dividing it into a quadrillion pieces, and you begin to approach how faint these cosmic fields are. But faintness is not the mystery. The mystery is reach. These impossibly gentle fields stretch across the voids between superclusters, across regions so empty that they contain almost nothing at all, persisting as remnants of some process that operated before the first structures ever formed. A field that weak, spread across a space that enormous, cannot have been made by any ordinary means because there was nothing ordinary there to make it. So where did it come from? This is where the story reaches back toward the beginning, and possibly past it. Because no known process occurring after the Big Bang can easily generate magnetic fields across such enormous empty volumes. Physicists have been forced to consider that these fields are primordial, that they were seeded in the earliest moments of the universe, and then stretched and diluted to their present faintness by billions of years of cosmic expansion. And when you ask exactly how early, the answers reach further and further back. Some models suggest the fields were generated during cosmic inflation itself, during that burst of exponential expansion in the first tiny fraction of a second, when quantum fluctuations were stretched to enormous size along with everything else. Other models trace them to phase transitions in the early universe, moments when the fundamental forces of nature separated out from a single unified force into the distinct interactions we know today, and each such transition could have left magnetic seeds behind. And some models push the origin further still, to conditions that existed before inflation, in an epoch of physics that remains entirely theoretical, a chapter we can describe only in equations we're not yet sure how to trust. On that reading, the magnetic threads running through the emptiest spaces in the cosmos are older than inflation, older than the event that shaped everything we can observe. Let me try to make this less abstract. Imagine drifting through one of the great voids between superclusters, a region so empty you could travel for tens of millions of light years and pass almost nothing at all. No stars near enough to see as more than points, no gas to speak of, just emptiness in every direction, more thoroughly empty than any place you can picture. And yet, threaded invisibly through that emptiness, there is a structure, a magnetic framework, unimaginably faint, holding a shape, remembering an orientation that was set when the universe was younger than a heartbeat, and possibly before it began to expand at all. You would feel nothing. You would see nothing. And you would be moving through the oldest scaffolding there is, a web within the web, invisible, silent, older than the light of the first stars. These fields are not idle. They have shaped the way gas flows between galaxies. They have guided how cosmic rays, the fast particles that stream through space, travel across intergalactic distances. They influenced how the first stars and galaxies assembled out of primordial matter. The magnetic architecture of the cosmos was laid down before any of the structures it would later shape existed, and then those structures grew up inside it, guided by a framework they did not create and could not see. We are, in a real sense, living inside a magnetic pattern that was strung across the universe in its first instant, or possibly before that instant, and we are only now building instruments sensitive enough to detect that it is there at all. To place these fields properly among the ancient things, it helps to see how quietly they have kept their secret. A magnetic field is not a substance you can weigh or a light you can catch. It is an orientation of space, a direction, and a strength written into a region, invisible unless something charged happens to move through it and get nudged. For most of the history of astronomy, we had no way to sense such a thing across the emptiness between galaxies, because there was nothing out there to be nudged that we could watch. The fields could have been threading the voids the entire time and we would never have known. It was only when we learned to use the universe's own high-energy particles as probes, watching how their paths and their afterglows are subtly altered, that the hidden framework began to reveal itself. In other words, these fields are not new. They have been there all along, older than the galaxies, and we are simply the first generation able to notice. And notice what kind of oldness this is, because it is different from everything before it on the list. The neutrinos are old, but they move, streaming past us and away. The frozen sound is old, but it grew, stretched by expansion into something enormous. But a magnetic field in a void is old and still, holding almost the exact orientation it was given at the start, because there is nothing out there to disturb it. No star has ever churned it. No cloud has ever passed through to twist it. It simply persists, diluted by the expansion of space but otherwise untouched, keeping a direction that may have been set before inflation. Of all the fossils on this list, it may be the most undisturbed, precisely because it lives where nothing ever happens, in the great emptiness where time passes and leaves almost no mark. It is worth understanding how you can possibly detect a magnetic field in a place that emits almost nothing, because the method is wonderfully indirect. The Fermi telescope does not measure the void's field the way a compass measures Earth's. Instead, astronomers watch extremely distant, extremely energetic sources, objects that fling out beams of very high-energy gamma rays across intergalactic space. As those gamma rays travel, they interact with the faint background light of the universe and produce showers of secondary particles, which should in turn produce a particular halo of slightly lower energy gamma rays around the source. But if there is a magnetic field in the intervening space, even an incredibly faint one, it will bend the paths of those secondary particles and smear out or suppress that expected halo. When astronomers looked, the expected lower energy glow was missing or altered in a way that pointed to a magnetic field threading the void. They found the field not by seeing it, but by noticing the shadow it cast on something else. From that absence, they could even estimate a lower limit on how strong the field must be. The reason a primordial origin is taken so seriously comes down to a problem of filling. We know how galaxies build up their own magnetic fields over billions of years through the slow churning of their gas, and galaxies can even blow some of that magnetized material out into their immediate surroundings through winds and jets. But the great voids between superclusters are so enormous and so empty, so far from any galaxy, that it is very hard to see how galactic outflows could ever have reached them and filled them uniformly. The fields are in places that galaxies cannot easily have seeded. That is what pushes physicists toward the idea that the seeds were already there, laid down in the early universe before galaxies existed, and then merely stretched and diluted as space expanded. A field that was present from the start would naturally end up everywhere, including the emptiest places, because everywhere was once packed together in the same tiny volume. The idea that magnetic fields could be born in the first moments even has a name, magnetogenesis, and it points at something profound about the young universe, that the early cosmos was not only hot and dense but electrically alive, full of charged particles in violent motion, exactly the conditions under which magnetic fields can be seeded. When the fundamental forces separated from one another in the opening slivers of time, or when quantum fluctuations were stretched enormous during inflation, magnetic seeds could have been left behind as a kind of birthmark of those events. If we could ever confirm which of these origins is correct, the intergalactic fields would become a direct window onto physics we can study in no other way, the physics of the first fraction of the first second, or of whatever came before it. The faint compass turning of the empty voids would be a record of the universe's first decisions about what kind of place it was going to be. If that is right, then these fields are among the most faithful messengers we have from the universe's first moments, because unlike gas and stars, which have been churned and reprocessed countless times, a magnetic field in an empty void has almost nothing to disturb it. It just sits there, holding its ancient orientation, stretched thinner and thinner over the eons but never erased. It is a fossil that has been left almost perfectly alone since the beginning, or before it, precisely because it lives in the one place where nothing ever happens. I keep returning to that phrase, before that instant, because it is where this entry crosses a line that the earlier ones only approached. Methuselah might be a measurement error. The quasars' seeds lie behind our horizon but still inside our universe. But these magnetic fields may genuinely predate inflation, and inflation is the event we usually treat as the shaping of everything. To say something came before inflation is to say it came before the moment we normally think of as the true beginning of the cosmos we know. And if a structure that faint, that enormous, and that old is woven through the empty spaces all around us, then the emptiness itself is not empty, and the beginning is not quite the beginning. The next two entries take that idea and carry it all the way. The first of them is a sound in the fabric of space that we have only just learned to hear, and part of it may have been made before the Big Bang. Part 9. The ringing beneath everything. We are close to the bottom of the list now, and the objects have been getting older, stranger and harder to see. We began with a star you could almost point to. We have passed relics from the first second, structures written before the first atom, magnetic threads older than inflation. And now we come to something that reaches back so far it may carry information from before the fundamental forces of nature had even separated, and possibly from before our universe began at all. It is a sound in the fabric of space itself, a constant low reverberation washing through everything, and we detected it only very recently. It is the gravitational wave background, and part of it may be older than the Big Bang. In 2023, several teams of astronomers around the world, working with instruments called pulsar timing arrays, announced a discovery they had been building toward for years. Groups including Nanograv in North America, the European Pulsar Timing Array, and the Parkes Pulsar Timing Array in Australia had all been watching the same thing, in different parts of the sky, and they all found the same signal. All of space, in every direction, is very faintly ringing. There is a low-frequency background of gravitational waves, ripples in the fabric of space-time itself, washing through the entire universe, a constant hum beneath everything. And some components of that hum may reach back to the first trillionth of a second after the Big Bang, and possibly from before it. To understand what they found, you have to understand what a gravitational wave is. Einstein predicted them in 1915 as a consequence of his theory of general relativity. Space-time, in that theory, is not a fixed stage. It is a flexible fabric, and when massive objects accelerate, they send ripples through it, stretching and squeezing space itself as they pass. For a century, these ripples were only a prediction, too faint to catch. Then, in 2015, the LIGO detectors caught their first one directly, a wave from two black holes colliding more than 1 billion light-years away, and a century-old prediction became an observed fact. But that was a single, sharp event. One collision, one burst. The gravitational wave background is something else entirely. It is not one event. It is the sum of countless events, overlapping, accumulated across the entire history of the universe, blended into a persistent, omnidirectional hum that is present at every point in space at once. Much of that hum comes from a source we understand reasonably well. Across cosmic time, supermassive black holes at the centers of galaxies have spiraled together and merged, and each of those mergers sent out gravitational waves that are still traveling. Add up all those mergers, across billions of years and countless galaxies, and you get a background rumble, a low tone made of many overlapping sources. That is the leading explanation for most of what the pulsar timing arrays detected, and it is remarkable enough on its own. But it is not the part that concerns us tonight. The part that concerns us is the possibility hidden underneath the black hole mergers, the most ancient component of the hum, the one that may reach back to the very first instant. Because gravitational waves pass through matter almost untouched, they can carry information from epochs that light can never reach. Light cannot show us anything from before 380,000 years, because before that the universe was opaque, a fog the light could not cross. That is why the cosmic microwave background is our earliest picture. The neutrino background reaches further, back to 1 second. But primordial gravitational waves could, in principle, carry information from as early as 10 to the minus 36 seconds after the Big Bang. That is a number so small it has no meaning in ordinary experience, a fraction of a second so tiny that the fundamental forces of nature had not yet differentiated when the universe existed in a state our physics can only approximate. If inflation happened, it should have generated gravitational waves, and those waves would be the oldest signal it is even possible to receive, a message from the first flicker of existence. And some theoretical models go further, to the edge of what we can responsibly say. They suggest that the gravitational wave background might contain imprints of processes that occurred before the Big Bang itself, in whatever state preceded our universe's expansion. If our cosmos emerged from a previous contracting universe, a great collapse that bounced into a new expansion, or from a quantum fluctuation in a larger multiverse, then the gravitational waves generated during that transition could still be propagating through our space-time right now, carrying information about a reality that existed before our reality began. On that reading, we may already be soaking in the faint reverberations of a universe that came before ours. To understand why this entry sits so near the bottom of the list, you have to understand what gravitational waves can do that nothing else can. Every other messenger we have discussed has a wall it cannot cross. Ordinary light cannot show us anything from before 380,000 years, because before that the universe was an opaque fog, and light could not travel through it freely. That fog is the reason the cosmic microwave background is our earliest picture, a curtain we cannot see behind with light of any kind. Neutrinos push the curtain back further, to 1 second, because they slipped free earlier, but gravitational waves answer to no curtain at all. They pass through matter almost untouched, which means they can travel to us from epochs no light could ever escape, from times so early that the universe was still opaque to everything else. They are the one messenger that could, in principle, carry a signal straight out of the first instant. That is what makes the faint oldest layer of this hum so precious and so tantalizing. If it is there, it is a signal from a time we can reach in no other way, from a fraction of the first second, from before the fundamental forces had even separated into the distinct interactions we know. Nothing else we can build or imagine could bring us news from that moment. Light cannot. Neutrinos, in practice, we can barely catch even from 1 second. But a gravitational wave from the first flicker would arrive, having passed through everything in between, as though it were not there, still carrying its ancient shape. It would be the closest thing to a direct message from the opening of existence that physics permits. And the boldest possibility of all is that some of the signal was made before the opening, in whatever preceded our universe's expansion, a message not merely from the beginning but from before it. The way we detected this hum is one of the most elegant ideas in all of modern astronomy, and it is worth understanding because it turns dead stars into the most precise clocks in the universe. When certain massive stars die, they can leave behind a rapidly spinning remnant called a pulsar, which sweeps a beam of radio waves across space like a lighthouse. Some of these, the millisecond pulses, spin hundreds of times per second with such astonishing regularity that the pulses arrive at our telescopes with a steadiness that rivals the best atomic clocks on Earth. Now imagine watching many such clocks scattered across the sky at once. If a gravitational wave rolls through the space between us and those pulses, it very slightly stretches and squeezes that space, which means the pulses arrive a tiny bit early or a tiny bit late, by mere billionths of a second, in a pattern correlated across the whole sky. That is what the pulsar timing arrays spent years, in some cases decades, painstakingly measuring, and in 2023 they announced that the correlated pattern was there. The universe was ringing, and they had heard it by watching dead stars flicker. Sorting out what is producing that hum is the great task now underway. The leading and most conservative explanation is the collected rumble of supermassive black holes spiraling together across cosmic history. And if that is the dominant source, it is already a landmark discovery, a confirmation that these colossal mergers happen and leave a background trace. But teasing apart the layers of the signal, separating the black hole rumble from any older, more primordial component beneath it, will take much more data and many more years of patient listening. The cosmological layer, the part that might reach back to the first sliver of the first second, or beyond, is not something we can cleanly pull out yet. We know the hum is real. We are still learning to read its oldest voices. There is a related hunt worth mentioning, because it shows how badly we want to hear the first instant. If inflation happened, it should have stamped a very particular kind of gravitational wave onto the ancient light, a faint swirl in the pattern of the microwave background that would be a direct signature of the universe's first flicker. Teams have been searching for that swirl for years, and there was a famous moment in 2014 when one group believed they had found it, only for the signal to turn out to be dust in our own galaxy, dressed up as a cosmic message. The search continues, more carefully now. Whether through the ancient light or through the hum in the pulsar timing, the prize is the same, a direct signal from the opening instant of existence, and possibly from before it. We have decided the first moment is worth listening for, and we have built instruments patient enough to spend decades in the attempt. Let me take you into that possibility for a moment, gently, because it is worth feeling. Lie still and picture the space around you, the ordinary quiet air of the room. Now understand that this space, all of it, including the space your body occupies, is very faintly ringing. There is a background tremor in the fabric of space-time, so slight that it took watching distant dead stars flicker for decades to reveal it, washing through you and everything else without pause. Some of that tremor was made by black holes colliding across the ages, but some of it perhaps was made in the first sliver of the first instant, before the forces of nature had separated. And a part of it, if the boldest models are right, may have been made before our universe existed at all, in whatever came before the beginning. You're not hearing it from somewhere far away. You're inside it. It is passing through you, the way the neutrinos pass through you, a second ancient tide you cannot feel, and buried in its faintest layer, there may be a sound older than time, a reverberation from before the first moment, reaching you now in the dark. It took an almost unreasonable kind of patience to hear this at all, and that patience is part of the wonder. The teams behind the pulsar timing arrays watched their sets of dead stars for years, some of them for more than a decade and a half, measuring arrival times to billionths of a second, slowly separating a real cosmic signal from every possible source of noise, from the wobble of the Earth to the churn of the interstellar medium. What they were listening for was so faint that it could only emerge after 15 years of steady watching, a hum that had been washing through the space around us the entire time, present in every second of every one of our lives, and utterly beyond our notice until we built the patience to hear it. It had always been here. We simply could not listen slowly enough until now. What message is written into the faint ringing that fills every point of space? And if some of those waves truly carry information from before the Big Bang, are we ready to confront what that information might tell us about the true nature and origin of existence? We do not yet know how to separate the ancient layer of the hum from the black hole mergers laid over it. But the fact that the layer might be there at all, that a signal from before the beginning might be washing through us this very second changes what the word beginning even means. And that brings us to the final entry, number 1, the oldest thing in all of our models of the cosmos, the one thing that had to exist before the Big Bang for the Big Bang to happen at all. Part 10, the field before the beginning. We have arrived at number 1, and to reach it we have to leave behind the idea of objects entirely. Every other entry on this list has been a thing, or a relic, or a pattern, something within the universe, however old. But the final entry is not within the universe. It is the thing the universe came out of. It is older than the Big Bang because it had to be there before the Big Bang for the Big Bang to occur. It is the most ancient entity in all of our cosmological models, and its most disturbing property is that it may not have originated in our universe at all. It is called the inflaton field. To understand it, we have to go back to a problem that troubled cosmologists for a long time. When we look at the universe on its larger scales, it is astonishingly uniform. Regions of space on opposite sides of the observable cosmos, so far apart that light could never have travelled between them, nevertheless have almost exactly the same temperature, the same density, the same properties. This should be impossible. How can two places that have never been in contact, that have never exchanged so much as a single particle of light, be so perfectly matched? It is as if you found two people on opposite ends of the earth who had never met and never communicated, wearing identical clothes and speaking identical sentences at the same moment. Something had to connect them. In 1980, the physicist Alan Guth proposed an answer, and it reshaped cosmology. He suggested that in the first fraction of the first second, the universe underwent a period of almost unimaginable expansion, growing exponentially, doubling in size again and again in a sliver of time. This is cosmic inflation. Before inflation, the entire observable universe was packed into a region smaller than a single proton, small enough for every part of it to be in contact, to reach a common temperature and density. Then inflation stretched that tiny uniform patch to something larger than the observable cosmos, in roughly 10 to the minus 32 seconds, carrying its uniformity with it. The reason distant regions match is that they were once neighbours, before inflation flung them apart. It is an elegant solution, and it has held up remarkably well. But it raises a question that reaches past the beginning. What drove the expansion? The answer is the inflaton field. It is not matter, it is not radiation, it is a quantum field, a kind of energy that filled all of existence, sitting in a high-energy state, and it was this field that drove the stretching of space-time itself. When the field finally released its energy, when it decayed out of that high-energy state, the enormous energy it had been holding poured into the newborn universe and became the matter and radiation that would go on to form every particle, every star, every galaxy, and every atom in existence. In a very real and literal sense, the inflaton field is the origin of everything. The universe as you know it, all of it, is the debris left over from the decay of that field. Every atom in your body was, at the beginning, energy stored in the inflaton field, waiting to be released. Now hold on to the sequence carefully, because this is where the oldest thing on the list earns its place. The inflaton field had to exist before inflation. It had to be present before the universe expanded, before space-time took on its current structure, before the fundamental forces separated into the distinct interactions we know. It is not a product of the Big Bang, it is the precondition for the Big Bang. The Big Bang emerges from it, and that means the inflaton field, or whatever generated it, predates our universe entirely. It belongs to an era of physics beyond our observational horizon, and possibly beyond our theoretical understanding, a time before the beginning in the most complete sense those words can carry. It is worth understanding just how much work this single field is asked to do, because that is what makes it so central and so strange. The uniformity of distant regions was only one of the puzzles it solved. There was also the question of why the universe is so precisely balanced, so close to perfectly flat in its geometry, when the natural expectation would be for it to have curved wildly one way or the other. Inflation answers that too, because stretching any surface by an enormous factor flattens it. The way the ground beneath your feet looks flat even though the earth is round, simply because you are standing on a tiny piece of something enormous. Inflation takes whatever curvature the infant universe had and stretches it smooth, and in one more remarkable turn, the same field explains where all the structure came from, because tiny quantum fluctuations in the inflaton field itself stretched to enormous size during the expansion, became the very density variations that later grew into galaxies. The seeds of every galaxy may be the frozen quantum jitter of the field that predates the Big Bang. When inflation ended, the field had to hand its energy over to the ordinary contents of the universe in a process sometimes called reheating. The high-energy field decayed, and its stored energy poured out as the hot bath of particles and radiation that we think of as the traditional Big Bang. So in this picture, the fiery beginning we usually imagine, the hot dense state, was not truly the first event. It was the second act. It was what happened when the inflaton field released its grip. The fire came from the field came first. That single reordering changes the meaning of the word beginning in a way worth sitting with. For most of human history, and even through much of modern science, the Big Bang stood as the first page, the moment before which the question what came before had no meaning. But if inflation is right, the hot Big Bang is a consequence, an after effect, the decay product of something prior, and the thing prior, the inflaton field, is not a moment at all. It is a condition, a state that had to already be in place. You cannot have a decay without something to decay. You cannot have an end of inflation without an inflation, and you cannot have inflation without the field. Step by step, the logic forces the origin of everything backward, out of the fire and into the field, and the field sits on the far side of the beginning, and it may not be unique to us. In a framework called eternal inflation, developed by the physicist Andre Linde and others, the inflaton field is not a one-time event that happened only in our cosmos. It is a permanent feature of a much larger structure, constantly generating new universes through quantum fluctuations, endlessly. In that picture, our entire observable universe, 93 billion light-years of galaxies and stars and planets and empty space, is a single bubble in an infinitely larger, endlessly inflating substrate. The inflaton field would be the medium in which all possible universes form, the ground from which every reality bubbles up. It existed before our universe. It will persist after our universe reaches its final cold silence, its heat death. It may in fact have existed forever, with no beginning of its own at all. I want you to feel the full inversion of significance this represents, because it is the emotional destination of everything we have said tonight. We think of the universe as everything that exists. It is the container of all things, the total of reality. But if the inflaton field is the true substrate underneath it, then our universe is not everything. It is a temporary fluctuation in something vastly older and incomprehensibly larger. The Big Bang was not the beginning of existence. It was a local event, a phase transition in a field that stretches beyond anything we can observe or measure or perhaps ever comprehend. Every particle in your body, every star in the night sky, every galaxy in the observable universe is a passing pattern, a brief arrangement in a field that predates all of it and will outlast all of it. Remember the star we began with, 190 light-years away in Libra, and the phrase that troubled us then, older than the universe that contains it. We said that of Methuselah as a paradox, a contradiction, almost certainly a measurement error. But here, at number 1, that same phrase stops being an error and becomes the plainest truth there is. The inflaton field really is older than the universe that contains everything, because it is the thing our universe came out of. What began as a mistake in our clocks ends as the deepest fact in our physics. And the caveat we admitted at the very start, that we cannot prove the oldest things formed after the universe began, turns out not to have been a footnote at all. It was the thesis. It was where we were always heading. There is a question that naturally rises here, and honesty requires that we sit with it rather than pretend it away. If the inflaton field predates the Big Bang, then what made the inflaton field? And the truthful answer is that we do not know, and that our physics runs out of road before it can tell us. We can describe the field, we can write down how it behaves and what it does, but its ultimate origin lies in a regime where the theories we trust break down, where the ordinary ideas of before and after may not even apply in the way our intuition demands. Some physicists suspect that at that boundary the very notion of time as a smooth flowing thing dissolves, so that asking what came before the field may be like asking what lies north of the North Pole, a question that sounds sensible but has no direction to point in. We have followed the chain of causes as far back as it will go, and at the end of it we find not a final answer, but the edge of what can be asked. That is a humbling place to arrive, and it is worth noticing that it is exactly where this entire list has been leading. We began with a star whose age was probably just a measurement error, a tidy puzzle with a reassuring resolution, and step by step, object by object, we have descended from problems we can likely solve, through relics that genuinely predate our sight, to a final entity that predates the universe itself, and whose own origin lies beyond the reach of our physics. The list is not really 10 separate curiosities. It is a single staircase, and it descends from the merely surprising to the genuinely unknowable, from a smudge on the timeline to the admission that the timeline may have no first step at all. The beginning, which we started out treating as a solid wall, has come to look more like a horizon, the edge of what we can see rather than the edge of what there is. So let me leave you with the reorientation rather than the fear, because this channel has never believed the universe is something to be afraid of. Lie in the quiet and consider that you are made of the debris of a decayed field older than time. The relic neutrinos from the first second are passing through you as you rest. The faint gravitational tremor, part of it perhaps from before the beginning, is washing through you too. The magnetic threads older than inflation stretch across the emptiness beyond your window, and underneath all of it lies the inflaton field, the substrate, the thing before the beginning. We are not, it seems, inhabitants standing on top of the cosmos, looking out at it as something separate from ourselves. We are momentary patterns within something we cannot see, cannot measure, and may never fully understand. Something that existed before the beginning, and will persist long after everything we know has dissolved back into the quiet from which it briefly emerged. And there is a strange peace in that, if you let it settle. To be a passing pattern in something that old is not only to be small, it is to belong to the oldest thing there is,